Ladies and gentlemen, please welcome MIT computer vision scientist Ramesh Raskar.
Hello. Can you imagine driving through fog as if it's a sunny day? Can you imagine reading a book without opening it page by page? Or can you imagine tracking circulating tumor cells through a device that looks like a blood cuff? Now, for all of this, the key is time. Now, this video projector and the optical engine inside it is controlling light every millimeter at every millisecond. But imagine if we can conquer time and we can control energy every femtosecond at every femtometer. And that's femtography. Now, at such small quantities of time and space, and all the scattering that you would imagine while driving through fog or reading a book, there's going to be a lot of noise. But the message is, one man's noise is another man's signal. Now, 3 years ago, our team at MIT showed how we can use femtophotography to create these movies of light in slow motion. We use a femtosecond laser and send packets of photons into this bottle, and the photons scatter through the bottle. You see the energy fronts propagating on the table. Most of the photons hit the cap of the bottle, and they explode. At the top, you see there's a pocket of air where the light is bouncing around. And after several picoseconds, you see at the back of the bottle a concentration of light because of the parabolic curvature of the bottle, right? And of course, this movie is virtually 1 nanosecond. That's how long it takes light to travel about a foot. But in reality, we have to capture this scene by sampling it millions of times because we just don't have enough signal. It's mostly noise. OK, so it's great for direct view. And from that, we can create these femto photos, which are time-lapse isochrone contours, where the separation between time-lapse is about 25 picoseconds. So what can we do when we can start processing light at such speeds? First of all, to acquire that, we use trick tubes that map time to angle. And typically, they're used for spectroscopy. So we repurpose the electronics, the triggering, the computation, so that we can create these movies. But to capture that movie that you saw for the bottle, it takes about an hour. Okay? So I think the Coke bottle movie looks really good. But we did get a call from Pepsi of why didn't we use their bottle? All right, so the data we get is this space-time images where most of the information is actually in the scattered light. So instead of thinking about first photon imaging, let's start thinking about all photon imaging. Let's try to use all the information that's coming at us. And with that, can we see around corners beyond line of sight? The trick here is to use multiple bounces of light. You shine light on the door, it reflects in the room, part of the light comes back and back to the camera, and by analyzing that, we can see around corners. So this is our femto camera, and our goal is to see this hidden mannequin, and we're going to use our laser pulses to emit packets of photon at what's visible. Let's use what we can. As the packet of photons hit visible surfaces, they start creating spherical shells of energy. And those shells hit the hidden object, which in turn create more spherical shells. The shoulder, the arm, the knees. And they return back to the visible surface, and they create even more spherical shells. Now, combination of all these creates photons, a tiny fraction of photons that actually come back. But interestingly, they come back with a very unique timestamp. right? So if we have a detector that can start processing this in femtoseconds or picoseconds, we can start making some sense of this conflicted information. Now, our resolution is just about 2 picoseconds. So although we know very precise distance to, in this case, to the head, we don't know whether the photon came from the head or the shoulder or the knees. And so we have to solve an inverse problem to actually recover the 3D shape of what's around it. And for that, we're going to create enough aperture diversity and shine the laser spot on multiple parts of the visible wall. And once you have done that, what do we see? We have a 3D shape of what's around the corner. Here, our working volume is about 30 by 30 by 30 centimeters, and we get a precision of about half a centimeter. All right. Now, you probably saw that Dr. Milokovic has a DARPA reveal program that has a similar spirit of how can we see around corners and solve problems at meters to kilometers range, right? And so we haven't built our system to take it outdoors yet, but when we do, we might be able to avoid collision of what's around the band, or look for survivors in hazardous conditions, or build new types of endoscopes that can have a very interesting insight inside the body by exploring multiple channels simultaneously, not one at a time. And then also solve problems because of scattering, if you have tissue and blood and so on, so that we can do this inversion even in presence of significant scattering. So let's look at this one at a time. The first question you would ask is, whoa, looks like your noise is going to dominate your signal. Absolutely right. And how are we going to deal with materials? Well, there are multiple ways you can deal with it. Imagine if you can walk into this room, take a picture from a single viewpoint, and start identifying what's metal, what's dielectric, what's fabric, what's skin, and what's glass. Typically, you would do that by using spectrum, by using wavelength. But in reality, there is another well-known way to identify materials, and that's called BRDF, bidirectional reflection distribution function. And this reflectance function actually also classifies different types of material. And for that, we need incoming and outgoing pairs of direction for shining light and observing the outgoing radius. And so our group showed a few years ago that indeed you can do that, in this case by shining light on the left wall and recording the image on the right wall, if you want to get the material property of what's on the far wall. So you can play these tricks as well. And in some cases, you can work in regimes where the noise is extremely high. Dr. Facio's group in Scotland, we're working on single photon sensitive images. So the Coke bottle was through repeated measurements as well as using streak sensors. And here we go using SPAD arrays. And all of us who are mesmerized by Princess Leia and see how we can see light in midair, creating images, finally, we can see them. So here you have, again, a femtosecond pulse that enters this volume. And now we can see the effect in midair without any additional dust particle or any other intervention. And what about plasma? When you actually see change in wavelength, you actually see nonlinear effects. So here again, start with a femtosecond laser in 800 nanometer. But as you can see, it turns into a 400 nanometer output, a nonlinear effect that we can observe through these mechanisms. Now, we are always dealing with scattered light. It's not just about mitigating the light, mitigating the scattered light, which is what we do using gating or doing OCT and so on. But here, in fact, we want to exploit. We want to become friends with scattered light. And I would say another trend is how do we actually start creating scattered light so we have more information about the scene. So what if you want to start looking at circulating tumor cells inside the body? Now, a common technique is to tag them with fluorophore and measure its fluorescence lifetime. The challenge is that the decay in energy is confounded by two different factors. One is how far away are the fluorophores from your measurement device, because they're scattering in between. So you see a decay there. And you, of course, see the decay because of the lifetime of the fluorophore itself. So you need a clever mechanism to disentangle the two. So what are the baby steps we're taking in this direction? We're able to use this ultra-fast imagery and ultra-fast detection and sweep across different wavelengths and frequencies to actually decouple these confounding factors as well. And can we create imagery inside oral imagery without using X-rays? And for that, we can again use all-photon imaging to see diffusers that could be as thick as 1.5 centimeters and recover the information behind that. So this time-resolved imaging is a new friend that allows us to see the world in very, very unique ways. OK, let's come back to how can we read a book without opening and reading it page by page. Now, in this case, we again want to send a signal and look at the reflected energy and analyze that. But most of the information actually is in the scattered light. We're going to use terahertz waves in this case because they can penetrate deep enough. But again, we're going to use the time dimension. Now, although terahertz can penetrate the book, there are many challenges. First of all, the terahertz are in 300 micrometers to a millimeter wavelength range, while the pages are 20 to 30 micrometers. Now, the contrast between the pages and the ink, because of the Fresnel reflection change in refractive index, is only about 4%. So the contrast is very, very low. Because of dispersion, different terahertz waves are going to mix in unmodeled ways. And probably the most interesting in this case is that the letters are going to occlude each other, and they're going to create effects that need to be removed iteratively. So here is what we have. These are our baby steps. Instead of reading a book, we're just going to read 9 pages for now, OK? So stay with me here. So we're going to take 9 pages and combine them with highly strong occlusion between them. We're going to pack them really, really tight to make sure there is enough complexity. And then we're going to use time domain terahertz to look at reflected signature. So we start scanning this signal. And as you'll see, we have to repurpose the way the signals are measured. And although the raw signal may not make sense, we're able to use this hypercube of data to start recovering individual letters. Now, you have to remember that in terahertz, which is electromagnetic spectrum, and not a surprise, it doesn't behave like light. You don't just have intensity, but you have phase. And you get phase reversal as you go through the air, paper, ink interfaces. So it's not as obvious as just looking at the peaks of a signal and marking them as a possible ink for your letter. So here's what we have. On the left, you see that in about a very narrow packaging, a very tight packaging of these papers, you can start recovering the pages even if they're not planar, even if there's a curvature on it. And then separately, we can go through point-by-point signals and look at the scattered energy and start making inference on what could be around that point, not just at the point at which you're probing, but what could be around that point. And the combination of that allows us to start recovering these 9 pages. So I guess we're not reading a book. We are kind of reading through an envelope right now. All right. What about other electromagnetic spectrum? What about using time in radio frequencies? Now, radio frequencies can penetrate through non-metallic walls very easily. So can we start using time domain information to recover shapes that are occluded from the line of sight as well? So here you see, again, a movie very much like the Coke bottle movie, energy propagating through the scene and reflecting and coming back. In any single frame is not very meaningful. And And there are a lot of challenges in this because you have to consider how would you deal with the fact that the surfaces have only are mirror-like at the wavelength, radio frequency wavelengths, and also the apertures are too small to beat sufficient diffraction limit. So the combination of the two, it makes it very challenging for us to actually create a 3D model from pure radio frequencies. But as you'll see in the work that's coming out, we're actually able to use techniques from computational photography by exploiting surface normals, by exploiting multiple viewpoints, and also exploiting the dynamic range of our signals to create full 3D shapes. And in this case, our resolution is somewhat poor, about 5 centimeter volumetrically. All right, so coming back to driving through fog. Now, we can dial up the time resolution, or we can dial down. It turns out when the scenes are sufficiently coarse, like on a street, we can also start using off-the-shelf devices, like a Kinect, the Microsoft Kinect, that uses signals in the 100 megahertz range. And the time resolution is in nanosecond range as opposed to picosecond and femtosecond. But the techniques of playing with time are still somewhat similar because we can do homodynning or heterodynning with emitted and received signals to start dealing with scattered light versus the direct light. So to see through fog, we have to figure out the signal that's reflected from what's in line of sight, but also use the information that's coming from parts of the scene that are not in the line of sight. And the combination of the two allows us to make an inference on what could be out there from even in a foggy scene. So when it comes to playing with time, I think we have looked at nanosecond, picosecond, femtosecond. The question is, how far can we go? So imagine in the future, we're able to go to sub-femtosecond and femtometer resolution of control of light. What can we achieve? First of all, we'll be able to beat any kind of diffraction limits because at 1 femtosecond, light travels about 300 nanometers, and at sub-femtosecond resolution, we can start creating imagery that can have nanometer resolution. So this is an amazing, amazing promise. We can start thinking about negative light. If we can control the phase of the signal through its time traversal, then we can actually create constructive and destructive interference through any volumetric medium. We can start and use the same technique to start imaging and stimulating brain the way we want. We're right here in St. Louis. Professor Li-Hong Wang is looking at photoacoustics. And by manipulating femtosecond level time resolution, we can start triggering things biologically, chemically, and physically. And probably the thing that's most dear to us, our food. Our microwave ovens can potentially probe and sample and selectively cook the food the way we want. Now, if time is on our side, we can transform communication, we can transform how we image, and we can transform how we manipulate things chemically or biologically. Thank you.
Fantastic. Thank you, Ramesh. So interesting. Well, Arthi wanted us to play at the intersections of disciplines, and we've already heard about the topology of data and 3D time of flight, so I think we're off to a good start. If you have questions, you can come up to the mics. If you're sending your questions by Twitter using hashtag WaitWhat15, since we're not operating on femtosecond scales yet, you need to do that kind of before the talk ends so we can have the question. Don't do it now. If we don't have any questions at the mic right now, I'll give a few that we've gotten so far. People want more of what you can do with this. That's the main thing. So can you say a little bit more about what kind of capabilities the 3D time-of-flight revolution might actually allow?
I mean, we have seen in the X-ray domain at attoseconds, we can start doing X-ray crystallography, but most of those measurements are destructive. And I think in the optical domain, domain or using other electromagnetic spectrum, now we have the ability to probe the world in really unique ways. So at one end, you would say, hey, I just want to see the world, just have a direct view, look at chemical processes, biological processes at sub-femtosecond resolution. That's interesting, but the message here is really looking at the indirect, scattered, all-photon imaging, which is not just look at the world as it is, but try to look at the world that you cannot observe otherwise. And using computational techniques that my group and others have developed, I think we can marry the sub-femtosecond time resolution with advanced inversion methods.
Someone here?
David Mascareñas from Los Alamos National Lab. Can you elaborate on the nature of the reconstructions you had to do, especially for those first images you showed?
You're talking about looking around corners?
Yeah.
Yeah, so when you have to look around corners, the ability to recover the 3D shape, the math is actually very similar to cone beam tomography or CAT scan. So the wider the aperture you have, the more path diversity you will have and better resolution you'll have. The narrower aperture, you have a missing cone problem, and reconstructions will have corresponding artifacts. So in our case, what we have shown is that by using straightforward reconstruction methods, of course, you'll get very blobby shapes. But by using scene priors, assuming that it's an opaque scene with free space and some continuity of surfaces, we can actually get extremely high-quality reconstructions.
Thank you.
Bill Conley, program manager in DARPA STO. One of the big trends in our office right now is everything's going distributed. So what would happen if you started doing multi-static imaging using these types of techniques? Is anyone doing that?
Explain to me what is multistatic.
Or what, sorry?
You said multistatic?
Yeah, multi-static.
What is multistatic?
So one illuminator, but then put 5 receivers, for example. And
Right.
then you can build up, hopefully, a map faster.
Yeah, I mean, as you know, in VLA, very large arrays and so on, it's clearly to your benefit if you can sample the energy over a large aperture that allows us to, get closer to your diffraction limit or, improve the resolution of your reconstruction. So there are definitely benefits of those kind, but as I said, there are standard benefits that you get by playing with coherence or, making very precise time measurement. But the message here is to let's move away from those standard, I would say, specific benefits of having time resolution and start moving towards the scattered energy and see what we can do when it comes to fog or food or biological tissue out there. So I think there are a lot of benefits in thinking about time resolution on its own and using that for beam forming and so on. And there are additional benefits in thinking about everything else that doesn't fit your model.
Yeah, Matthew Schultz from Immusoft, a gene therapy company, and I was interested in how far you've been pushing the limits of this for cellular microscopy. So being able to effectively image inside a living cell non-destructively.
Yeah, so the challenge of a lot of these techniques is almost like the uncertainty principle, getting it right in time as well as in space. And that's, there are some fundamental limits to how much you can push that. I mean, cellular imaging is not that challenging because we're looking at, micron or multi-micron level imaging. And there are other groups that have shown, for example, by using optical coherence tomography or confocal imaging, they can get really good signals. We have done a lot of work in microscopy by looking at parallel sheets. But I would say if you're doing microscopy at cellular level, it's not as challenging right now. But if you want to get below that and start looking at chemical bonds, viruses, molecules, then I think we have some exciting challenges coming up.
And with just a couple of minutes left, I have one other question from behind the scenes. Someone was asking, what are the chances that your cameras or lasers that you're talking about here could be miniaturized to a handheld level? This is kind of question that's always close to DARPA's heart. If we haven't invented it, we've at least made it smaller than it used to be. What are the odds of pulling that off?
I guess that's why we are here. No question is a joke. I think when you look at the fundamental components of what we are trying to do, ultra-fast sources, which are mainly lasers, ultra-fast detectors, which are basically transform domain, which convert time into space or angle or wavelength. All these things are around, and there is no reason why they should be large. I mean, mapping time to angle is like a cathode ray tube, effectively. And we know how to do that. So I think the community simply needs to come together to solve this problem. So I'm very delighted and looking forward to conversations around how some of these problems and the REVEAL program that DARPA has just come out with has similar challenges on how can we actually exploit the scattered light in very unique ways. I think this is our time. I think scattered light will conquer time and will conquer scattered light with this community.
Fantastic. Thank you all very much.